So, all right, I think we're going. Well, good morning. Yes, sorry about the screw up yesterday. So I'm not sure exactly where I pushed the wrong button, but you can hear me now. So I will again cover what I tried to present yesterday, and hopefully we'll have time to continue on to 3.1 today. So we're dealing with inequalities, statements that say a value is not specifically equal to a number, but maybe our x value can be greater than a certain amount or has to be less than a certain amount. So we're dealing with all those expressions that might be built out of those symbols, right? Greater than or equal to, and so on. So if I just wanted to show a solution, specific number on a number line, that would just be a dot, a point. That one point is the solution. But what if I'm talking about a solution? Let's give us a little more room to work here. I want all the x's greater than or equal to 2. All right. So we have two ways that we're going to describe or notate the solution set. The set is actually an infinite number of possibilities, right? So we can't just list them all. So we have two methods that we're going to use. One is to show it on the graph, and then the other is to use what's called an interval notation, where we basically list the beginning and end points if we can, and some specifics about the symbols, the way we write it, put it that way. So greater than or equal to 2. So we have two possibilities for our starting point on the graph. We have either a solid circle, which we will use to imply that that point is included in the solution set. A 2 gets to be one of the answers. If I have one, and we'll do that here in a second, for instance, like how about x strictly less than, say, -2. If I have one where the point that I consider my endpoint is not itself included in the solution, it just has to be strictly less than, can't be the -2, then we use the open circle. Okay, and you'll see that in MOM. I think Tara, I think you posted a note. It's a little touchy getting that to work properly in MOM, but hopefully you can play with it and figure it out. So here I'm going to put a solid dot on my endpoint 2, and I want greater than everything in that direction. So I would just shade in that direction on my number line. And again, in MOM, they've got one of those little pencil tools where you click on your starting point and then you click on your end point, I believe. I played around with it yesterday. I think I found that if I started out here on the end, it would put the arrowhead on. And then if I went backwards to my starting point, you might say, then it filled in the line. I think that's the tricky part, playing around with the program to get that to work, to do what you want it to do. And then there's also a drop-down box for pick the solid circle or pick the open circle. This one here, my other example, I want all the x's that are strictly less than -2. So I want open circle on my graph around that point, and then I would shade everything this direction, where it's going on forever. So this is going to infinity. This is going on forever in the negative direction. We call that negative infinity. So that sideways 8 symbol flattens out a bit usually. We're going to need to notate that symbol in our next version of how we show the answer. MOM, I think, gives instructions to use two lowercase zeros, excuse me, O's, two lowercase O's. But I think the newer version of our program that we're using also has a drop-down box that actually lets you click on that symbol. So these are the basics of how we're going to graph these kinds of solutions. And then the second system is called interval notation. And here we basically show the beginning point and where it's going to, right? This one starts at 2, goes out to infinity, and then we close it in either brackets or parentheses. We use a bracket on the end if it's including that endpoint. So here I'll use a bracket to say that says the 2 is included. It can be a 2. Infinity is just a concept, goes on forever. It's not a specific value. We always put a parenthesis around the infinity side. Okay. My other one over here, strictly less than -2. We kind of always think left to right. So in a sense, you can say, oh, it's coming from negative infinity and goes up to the -2. All right, so try to write it this way. I bet Mom will call it wrong if you try to reverse it. But we don't use a bracket. In this case, we use a parenthesis to say the -2 is not itself included. You can get it as close to that -2 as you might imagine, you know, very, very small fractions or something, but it can't exactly be the -2. It has to be something less than that. So combinations of brackets or parentheses, and then always a parenthesis around the infinity end of that interval notation. So problems will ask you for a combination of, you know, graphing and an interval notation solution. Some of the homework problems I noticed in Mom actually give you a collection of possibilities in interval notation and ask you to identify which one of them, you know, multiple choice, right? Which one of them describes the graph? You know, so you got to figure out, oh, is it going less than? Is it going to negative infinity, or is it going greater than? Is it going to positive infinity? Does it include the endpoint? Does it have a bracket, or does it not include the endpoint, an open circle? All right, so that's,
hey, Steve?
yes.
So yesterday I was actually trying to do some of that work and write in those answers, but is the comma important when entering it into Mom?
I think it is. Yes, that's this is part of the convention, is putting that comma in.
Okay.
Okay. I suppose I could play around with it and double check, but if you've, well, if it didn't work for you, that might be why. Okay.
Okay.
Yeah. It's the way I've always learned it, always taught it. All right, so these are the forms of our solutions that we're going to try to boil our inequality statements down to. It's kind of like saying, oh, I want to get my equation down to this, because then I know that's the number. Well, all right, so then our inequality statements are going to look just like all the different equation complications that we've worked with. Right? Except it's going to have an inequality statement in it rather than just an equal sign. We're going to use all the exact same solving steps, add or subtract, multiply or divide, in order to boil that down to something that says x is greater than or equal to whatever we get. Except there's one situation, which I'll talk about next step here, where we have to know that something is changing, something's a little different. But otherwise, if you'll see here, here I have my variable, the extra added or subtracted piece, and another constant on the other. Here I would add 4 to both sides. Made up a problem that's going to give me a fraction answer, I guess. That's okay. Divide both sides by the 3. And x gets to be anything greater than or equal to a 3. Excuse me, 11/3. 11/3. So on my graph, here's where I kind of get lazy when I'm just doing this. Here's my 11/3. All right. Mom's pretty nice to you. I think you've got integers, whole number values to use. Greater than or equal to, notice I use a solid circle. I'm shading that way. Interval notation. There's my end point. And going to infinity. Okay. That would be how I would show those two versions of the solution for that. And so you could imagine we might just have to multiply or divide, variable, add or subtract something, simplify, distribute into our parentheses, move things around because I need all the variables on one side, all the variables on constants on the other side. All those things we've been doing in solving equations, we might have to do with an inequality. This next part, where here's the one thing that's different, all right? I start out with just numbers, where I say, well, I know 5 is less than 7, for instance. All right, you know that. And I can add anything to both sides. And it's still true. This relationship, this side is still less than that side. 7 is less than 9. I could subtract something from both sides and that relationship would stay the same. I can actually multiply both sides by a positive number and it's still true, right? It's still true. But look what happens if I multiply by a negative. Basically, I would say I've got a 5 and a 7 out on this end of the number line. If I make them both negative, it flips the relationship. What if I multiply them both by a -1? Now I've got -5 and -7 here. I usually don't even put that in yet because I know what's going to happen. Now what's the relationship between -5 and -7, right? -7 is farther left than -5. This one's the small one now. If I multiply by a negative, it kind of flips them over the number line, you might think, flips them over 0, and the direction of the inequality reverses. Anytime I multiply an inequality statement by a negative on both sides, I have to change the direction of the relationship. That's the big deal. That's different than what we usually do with equations. That and similarly dividing by a negative, right? If I divide both sides by a negative, the same thing happens. It's like multiplying by a fraction, right? If I divide by, and here I try to be careful in presenting, not to even do it at this step, because I know as soon as I divide both sides, this should change. If I divide both sides by a negative, it's going to reverse the relationship. -4 is greater than -5. So there's the special case that you have to remember and keep in mind when you're working with these inequality statements. Anytime you multiply or divide both sides by a negative, you have to change the direction of the inequality. Now I just did this with numbers, so you could actually see the relationship in the actual values. But when we're working with variables, you just have to remember to do that same thing if it happens. Multiplying or dividing by a negative. So I'm making up one where it's likely to happen, but I have to do that. Multiply or divide by a negative. Here's my variable term. Here's a constant that's added or subtracted. Actually, though I've written it, that's a positive, and then I'm subtracting the variable from it. But I would still tend to leave the variable alone and move the constant to the other side with the other variables. So I'm going to subtract 7. And so -2x is less than or equal to 4. Adding or subtracting, even if it's a positive number or negative number, that doesn't change the direction of the relationship. But now to get down to 1x, I'm going to divide by -2. And because of that, this relationship is going to switch. I always have to go slow. It's so easy to write that backwards. So used to say that left side was less than, but now the left side is greater than. And that boils us down to, messy. Our solution set is any value greater than or equal to a -2. Tried to make that line better and made it worse. Greater than or equal to -2. Started out as a less than, but because of that negative, it switched to greater than. My graph then, what I'm at, -2 is my endpoint. Might have a bunch of other stuff around it, but let's see. I get to be equal to that endpoint. Greater than means I'm going to make my arrow go that way. And interval notation. -2 to positive infinity. Parenthesis over there. There's the two versions of your solution for that. Okay. So I say it over and over, sorry, but yeah, just watch out for multiplying or dividing by negatives. Otherwise, it's all the same steps you've been doing. Just a couple more examples like this. Here's one where we have variables on both sides, just like that might have happened in our equations. We want to get all the variables to one side and all the constants on the other, just like we do with our equations, and then go from there, add, subtract, multiply, divide. Again, the constants over here, so I might move all the variables to this side. I'm going to divide by a negative number. It doesn't mean this always happens, but I guess I've been reinforcing this concept here, which means that direction gets switched. So negative divided by negative will be positive there, and I just made up an example that happened to have a fraction answer. Less than or equal to, oops, that is positive now, isn't it? And I'm going to negative infinity. It's kind of awkward writing it backwards like that. And the number line would be similar. Let's see, yes, solid point, 23/4, and we're going this way. There's another version of this graphing technique that we usually present in the classroom when everything you're doing is on paper and by hand. But Mom is using this particular convention with the open and closed dots. The other way to do this that we often teach is we utilize the same bracket or parenthesis that we do in the interval notation. So I would make this look like 23/4. You know, I put the bracket right on the graph, which is the same thing I get to use in the interval notation. That's kind of convenient, right? So the bracket implies it includes that point. And if it was a strict inequality with a parenthesis, I put the parenthesis on the graph. So either way is acceptable, a normal convention for showing these solution sets on a graph. Mom's using the dots. It's real easy. I think. Always reluctant to say easy. Again, they'll mix. You might get some with parentheses, things you have to distribute. Maybe I should just do one. Let me talk about, it's always good to reinforce good distributing rules. All right. Here's one that I usually say, oh, it's messier because there's more stuff to do. Well, here's a grouping, X stuck inside of it. I'm going to need to distribute to get rid of that grouping. it is a -2 times both of those terms. You know, -2 of those, minus times minus. You'll see some folks make that mistake of not carrying that negative sign to both of those pieces. All right. Over here, I have some like terms I could combine. All right. Variables and constants on both sides. So I think I'll choose to move the x's to this side. Subtract 5x's. And I'll have to add that 12, subtract that 12. Notice adding and subtracting, all the stuff I'm doing right now does not affect the direction of the inequality. I don't have to worry about it until I get down to this step. Oh, I have to divide, but I'm dividing by a positive number, so it doesn't change the direction. X should be greater than -18. So I just did that one just to point out, yes, you might have to do some simplifying to get down to that last step. Watch out for your distributing, distribute that negative in there. Strict inequality, so I would be at -18 with my parenthesis going to infinity and open dot on my graph, open circle on my graph. All right. Just like our equations, there's some weird ones that could crop up. They usually kind of hide the problem, or the weirdness, let's put it that way, about this situation by making you do a lot of simplifying before you get down to that point. But let's see if I can take that. Let's make it up. And I better do this right. Yeah. I got to make these numbers right if I'm going to make this up right away. All right. So I had to change that to make sure that my example is correct, put it that way. I'm going to distribute here 3x plus 9 greater than or equal to 3x plus 6. 3x's on both sides. It's kind of flags should maybe start going off here. Wow, that's what's going to happen. That's kind of weird, right? Let's assume, let's say I was trying to move all the x's to one side. Let's subtract these. I'm left with 9 is greater than or equal to 6. Is that true? Yes, 9 is always greater than 6. Notice there are no variables left in that relationship. All right. That relationship didn't depend on any value I put in for x. This one is always true no matter what value I would put in for x. So, and any real number, all real numbers. Any real number would work for x. On your graph, if Mom wanted you to graph at some height, you have to graph the entire line. And interval notation, everything from -infinity to infinity. So any number's going to work. It could happen, right? Well, there's the one where we have an infinite number of solutions. What's the other thing that happens? Well, sometimes we get no solution. And so, without getting too tricky, Here's one that says 3x plus 7 is less than 3x plus 4. Kind of made it simple. Start to see, oh, this is going to be similar to the last one, but it's going to be false. How to subtract the x's. I get 7 is less than 4. Well, that's not true. No number I could put in for x will ever make that part of the relationship true. It will never work. So this is no solution. All right, no solution. There is no interval, so you can't even show an interval. I'm pretty sure mom would set you up to, click no solution or infinite number of solutions, something like that. There's nothing to put on the number line. It would be blank. Also, there is no solution. So a couple, unusual cases, which we always have to address because you need to know where might things go wrong or where are the weird details, right? So that's sort of a quick recap. Really about half our time, that's good. On 2.7, working through the inequalities. It's not the biggest part of this chapter. You might see one on the chapter test, something like that. One of these solve this inequality statement. Be prepared to show the interval on the graph and use that interval notation. If you're okay with that, I'd like to change gears and look at 3.1. Excuse me here. I guess it was yesterday when I tried to say this or the day before. We put chapter 2 and chapter 3 together. Chapter 2 is all these equation solving techniques. Chapter 3 then presents us with applications. Eventually, you call them word problems, right? That we have to build the application, build the equation, and then solve the equation. So the first ones that we start out with are kind of trying to use those expressions that we have tried to get familiar with, translating from the verbal into the math. And then we try to write the equation that expression. The expressions will actually be a statement that says that expression equals something, right? So let's see if I can come up with a couple good ones here to use for examples, right? You might have even seen this kind already earlier in the chapter. So here's a statement. 6 less than 5 times the number is 13. What you want to recognize is basically the two different parts. There's this relationship expression, and then there's the what's it equal to, the is. The is always our equal sign. And so everything before it actually is this more complicated relationship, you might say, and then it is, or it's going to equal 13. So writing our equation, eventually that's going to equal a 13, whatever else we get out of all of this. 6 less than 5 times a number. Well, there's a variable in there. There's an unknown number. Mom often asks you to use a specific variable. Just be careful about that. 6 less than, well, that's subtract, all right? So 6 less than 5 times the number. Unfortunately, I think I saw on the test, some folks kind of putting that backwards, like 6 minus 5x. This is 6 less than that quantity. So you start with the 5 times the number and subtract the 6 from it. And I would get that equation out of this expression or that statement. Try to call it a statement now because it's a complete sentence, right? Not just a standalone expression. The expression that actually equals something. And I'm hoping we could solve that easily. Add the 6, divide by 5. We'll leave that at that, okay? Oh. Very similar shape to this one. I threw in the word sum this time to show we're going to add a couple of things together. The sum of 5 and 3 times a number. So I know sometimes it could be confusing. Is that the sum of 3 and 5 is 8? But that's really, hopefully you can see that that's connected. 3 times a number. There's one phrase, one part of that expression. It all goes together. The sum of 5 and 3 times a number is 35. What do you want to be able to get out of that sentence, that shape there? There's a few different forms, you might say, of these problem-solving steps or problems that we're trying to address, and so I'm trying to get through a little of everything, an example of everything. Okay. All right. Take a second, write that down, sort it out. One number is 3 more than another number. Well, actually, they're describing 2 different numbers that we don't know, but one is related to the other. If I call this other number my unknown, all right, the other one is 3 more than that. How could I describe that? 3 more than this unknown? How about x plus 3? So their sum is 25. So apparently if I add these 2 numbers together, it equals 25. Well, here's the original one, and here's the other one that's 3 more than that. See how that works? So like this was one expression and there was the other one. Now I've got some like terms to combine. 25. Now watch out for this one. I'm not sure, Mom might ask for the larger one, the smaller one, or put them in order from smallest to largest, or increasing order. I think I've seen that kind of instruction. But if I solve this, subtract the 3, I get 2x is 22. That means x is an 11. Well, if I want both numbers, one of them was the x, well, the other one was x plus 3. So I need to be prepared, put it that way, to find both values and present them if Mom asks for both numbers. Just read your problem carefully. Okay? Okay, I'm going to change gears here. I saw this in Mom, so I'm going to address this kind. We're actually going to see this kind of problem a lot in the next chapter, chapter 4. We're the relationship depends on a certain number of hours worked or how many miles you drive or something like that. Let's say, I'll see if I can write this out. You paid $100 to rent a car for a week. I have no idea what the ballpark is for renting these days. Let's see, the cost included, let's see, $25 fee plus 10 cents per mile. How many miles did you drive? Miles. What we have here is a final amount, all right? And that final amount that you arrive at is based on a combination of a fixed fee and then an amount that varies based on how many miles you drive. In the old days, we used to do, phone service problems like this, but nobody buys phone service like this anymore, right? There was a flat monthly rate and then 5 cents every long distance minute or something like that. Now cell phones, it's all included. But we want to, you need to be able to write an equation for this situation, and then it'll ask you to solve it. Now you can kind of try to do a lot of it in your head and say, oh, my final value I get by doing this and this and this and this. You can write that equation, but see if you can get into the habit, put it that way, to help us set up the next chapter. Look for that final amount. That's the number that you want to put a loan on one side. Like $100 is the result of this other stuff. This other stuff really represents the relationship, and I could use it over and over and over, depending on how many miles. Well, what is that relationship? $25 plus 10 cents per mile. I'll use an X, might be an M. Just watch out, see what mom might ask for. All right. So how many miles did you drive? That's what we're looking for, right? How many miles? There's your variable, how many miles? And I need to analyze your problem that way. What are you looking for? That's what the variable stands for. So this is, I'm trying to emphasize a common form. We want to see some amount that changes with the variable, maybe something fixed added, and finally we get, as a result, our total value. Now here, if I subtract my 25, and you get to use your calculator. So if I divide both sides by 0.10, dividing by 1/10, I think I get 750. And miles. If you were doing this on paper, it would be important for you to remember to put in your own units, put your units on that. Maybe even be asked to write a complete sentence. You drove 750 miles that week, something like that. Mom might actually fill it in for you. I'm not sure at this point. I think something like that probably is about as complicated as that at this point. And try to make up another one here, okay? Is that all right? You get enough of that? You copied that? let's see, without trying to figure out, well, what are these collectibles? Say you have a collection of some collectible items, and they are currently worth, oh, let's say, $250. Sorry, making this up here. You have a set of collectibles that are worth $250 originally. Okay, they were originally worth $250. Sorry, they lose $10 value every year and are now worth, making up nice numbers here, $150. How long have you had them? Not very good collectibles, they're losing value. But you like them. All right, see if I made up. I was trying to make one that had a negative sign in it here, okay? They're originally worth $250, but then they're losing $10 every year, and they're now worth $150. Now, you can probably do that in your head, say, oh, I have to figure it out. But we want to be able to write an equation that describes the situation. You could use it over and over again. So again, what's that final value that you want to kind of isolate? Well, the final value is what they're currently worth. Right? Final value is the 150. And that's the result of the starting value minus $10 for every year. Squeeze that in there, see if that makes sense. This value I have now is the result of starting minus this depreciation amount, right? Goes down a little bit every year. Some things do that. So solving how many years, right? How long have you had them? There's your variable. Here I would subtract the 250. Let's hear about the negative sign for a second. Negative 100 is negative 10x. Dividing by the negative 10. I got a value of 10 years. That's how long I've had them. Again, try to analyze or sort through the question and write an equation that describes the situation, and then you'll be asked to solve it. All right, how am I doing time-wise here? Oh, good. All right, so those were the couple real wordy ones. Okay. Put it that way, huh? And see. All right, a made up problem, but this is what I'm taking right from the mom homework, my version of it, right? A 60 centimeter long board is cut into 3 pieces such that the second is twice as long as the first, and the third is 5 centimeters longer than the second. Find the shorter piece. Good laser there. All right, think it through. What are we looking for? Well, we're looking for the length of one of the 3 pieces. and in particular the short one. But there are three different pieces that are described here, but they're all described in relation to one another. So we can still kind of just use one variable and then try to describe all the others in terms of this shorter one, which looks like it's the first one. Okay? Add them all up. Got to be able to think that through. Oh, they're supposed to add all up to the 60 centimeters. And then they, for some reason, get cut to different sizes. So I need three expressions for the different lengths of pieces. Well, we already kind of said one of them is just an x. What does the problem say for another relationship? The second is twice as long as the first. 2 times the first. That's the second one. Yeah, I hope that makes sense. And then the third is 5 centimeters longer than the second. So 5 more than this. Now there are 3 expressions all in terms of each other that describe the 3 different pieces. And they're all supposed to add up to 60. So add all 3 expressions together. All right, 1, 2, 3. Got a bunch of x's to put together and solve from there. 1, 2, 3, 4, 5 x's. I subtract my 5 and get 55. 5x and divide by the 5 and get, well, x is 11. 11 centimeters happen to be the x is the short one. That would be my answer there. So the chore, the problem is to come up with these different expressions, all in terms of one variable that describe the relationship there. And the last problem or two, I believe, in homework uses a concept of consecutive integers or consecutive even numbers, something like that. Yeah. If I think of the numbers, numbers in a row on a timeline, right? And here's one number. How could I describe the one that comes after it? Well, it's just one more, right? So the next one is x plus 1. So there's sort of the trick in this kind of problem is describing, how do you describe consecutive integers? If I want the next one, I still want to just use the same variable. Well, it's 2 more than that one. So the next one is x plus 2. So this kind of problem, very similar now to what I just did with the pieces in the board. They'll say something like 3 consecutive integers add up to a certain number. 3 consecutive integers. 3 expressions. I have to have an expression for each one of them. You add them together and they equal a final value. If it refers to, say, even or odd consecutive integers, even or odd, how far apart would they be? 2 apart. All right, if this is a 2, 4, 6, that's an x, and this one's x plus 2, this one's x plus 4. So if the problem describes even or odd, you've got to recognize you're jumping by 2. But again, the problem would usually asks you to add them up, or maybe you find their difference, but you add them up and it equals a final value. Okay, I'm going to leave you there with that. And for right now, let's leave the homework as it is. That is through this 3.1 due Monday night. If you're giving it a try and you're really, really stumbling, getting stuck, please always send me messages, emails. If I really see that it seems to be an issue and we need to address it more on Monday, we'll talk about it again on Monday. Okay. So do your best, continue working through that homework, and have a nice weekend. And I'll see you on Monday. Okay. Bye for now.